I would like to be able to see if code is actually running or not. Because sometimes we do a timing and we think we did something very fast, but really what happened was because we are just doing test code and we're not really producing any tangible output sometimes, the compiler can go ahead and remove a huge section of our code. And so what we really saw was the effect of not producing the output.
Hello, folks, and welcome to a new episode of Marco Code, more specifically solving the 1 billion row challenge in Java. It's been a while. As always, I need some help. So Casey, come on stage.
Hello, Marco. Good to be back.
Yeah, it's great to see you. So what I wanted to do is, because we haven't streamed for a while, I wanted just to briefly tell people what we've been up to as a quick recap, just to jump right in. What we had in the last episode, we tried to establish a baseline for reading in file content, but it was done without a Ramdisk. And suffice to say, I managed to set up a Ramdisk for this episode. TempFS, if anyone wants to know how I did it, also works on macOS relatively flawlessly. By the way, when you ask ChatGPT, for example, can you set up a TempFS file system on macOS, you'll get no, you can't, even though it has been released like 5, 6, 7 years ago. And if you ask it again and say, hey, by the way, I do think you actually can, then on the second try, it tells you, yeah, right, you can. Yeah, and then it'll give you the command. So in any case, we have a Ramdisk setup, which was the setup in the original exercise as well. And I want to do one thing. The naive solution, I have it here, because we want to read in the file sequentially all the lines of the file. And then, what we're going to do is, you saw the file, we have cities, we have temperatures. We're going to split, cities and temperatures by a semicolon. We get the city with a temperature. We parse it to a double. We do some summaries, put it into a sorted map at the end of the day, print it out. And that is the algorithm that we want to have, more or less. The problem is, if you run this naive solution, which I'm doing here, you'll find out that even just reading in all the lines of the file sequentially with the base JDK methods should probably take us roughly 30 seconds or 33 seconds, along those lines. Hence, what we wanted to do is, our approach is, we're going to start from the very bottom, meaning we established a baseline. How fast can we actually read in all the entire file content into Java bytes in that case, with a Ramdisk? And then we're going to iterate on that baseline and adding step by step even more of the algorithm. And we're trying to not stray away too far from that baseline we have established. Does that sound all right, Casey?
Yes, it does. That's exactly what we want to do. And again, the reason that we need to do this is because without having a baseline to work from, we will never know how close we are to an optimal solution, right? It may be very easy for us to think, we got twice as fast as the naive solution or something like that, so we must have done a great job, but it turns out that the naive solution was like 100 times slower than it should have been. So the reason for the baseline and working from machine specifications backwards, basically, is not only does it tell us, how close we're to optimal, but it also lets us know everything we don't know. So every time we see ourselves fall off the baseline and by how much, that allows us to do an investigation to find out why, and that's how we actually learn about performance. And the more often we do that, the less often we have to do that, because our knowledge builds up and we can just know, like, oh yeah, don't do that, do this, and so on.
Exactly. And let me just add, as from my experience from project work I've done, this bottom to top approach essentially with performance is rarely what I've seen people do in real life. So usually what you have is you have some super slow program. For example, for whatever reason, as part of a workflow, you spawn, 500 SQL queries, and then you try and, condense these 500 SQL queries into 50 less, and you're happy when you come up with 350 queries at the end. But nobody asks themselves, as some sort of an overgeneralization, hey, how many SQL queries, for example, do I actually need? Maybe just one or two, and build up from there.
And how fast should those queries run? Are those queries running as fast as they should be running? All that sort of stuff. And that's the difference between sort of, a I'm just trying to get some speed increase, and I'm not trying to optimize this thing. I don't have very much time, and this is all I can afford to do is make some random changes and see how they go.
Yep.
Which sometimes is okay, but most of the time that's not a very good approach, even, when you're in a production environment. And that's because also you don't really know if that's going to work. You make some changes, maybe it doesn't get any faster, right? And so now you've wasted this time kind of just doing it instead of actually working through the problem where you'll make at least some progress. So I try to teach people to do it this way, and especially like we're doing now when we're trying to learn about performance, the random change method is not a good method. You want to work backwards from machine specs.
Right, let's do it. Which means back here, you can see I have my Ramdisk specified here, my file in a Ramdisk specified here. Just once more, I have a couple of different ways of reading in the file. There's essentially 3 ways. There is the good old Java 1.0 way of reading in the file. There's a file channel way, the new IO. There's also the memory map file. I just want to briefly run through these methods again to show you what kind of speeds we're getting. And the interesting thing is now, as you saw with the old buffered input stream, it took us roughly 1.1 seconds. Let me just rerun it with the file channel here. It should take maybe around the same time. It's roughly just depending on how often you run it, a couple of milliseconds here and there. With the exception of memory map files, to be honest, memory map files take us, let's see, 2.5 seconds, at least the code I wrote.
Yes.
And here, the interesting thing is, by the way, for me, what I noticed when I run this on my Ramdisk, actually the speeds are the same, roughly the same, as if I read in the file from the file system a couple of times, and the file system cache actually warmed up. They're roughly around in the same range. So there's almost no difference compared to the pure Ramdisk in my case. That's what I've noticed so far.
And that seems very reasonable, right? One of the reasons that we want to do this test, of course, is just to verify that there isn't anything lurking in that Ramdisk sort of architecture that's going to change our approach. So the reason I wanted to make sure we're getting some experience with that is because if the challenge specifies Ramdisk, and really, since this is an optimization challenge, really we want to run this on the exact target machine because we're trying to win a prize or something, right? We're trying to do it more as an exercise, so we're targeting a machine we have. We're not going all the way there. But just to show how the approach works, it's possible sometimes that a Ramdisk could be implemented differently in the operating system. But even if it's not, like you said, file cache is another thing that we do care about even in practice. So even if we're not looking at a challenge. And the operating system can choose to do different things. When it memory maps a file, it may or may not have a fast path for doing that if the file is already resident. And just to explain what that means, because there was some question about this on Twitter, actually. When you memory map a file, there's different ways that could work. It could be that what happens is the operating system just kind of, takes the amount of memory space that it's going to need for that file mapped into your process address space, and it will just kind of reserve it. And then when you touch any individual page of that, it will then fault, it'll actually stop, it'll wake up, and it'll go do the read, and it'll resume to you, right? And that can be very slow. That's not as good as doing some kind of asynchronous I/O, and you may even need, if you want to go that route, to do asynchronous I/O with that, so you touch the page on different threads. There's all these sorts of things you could do there, right? But it's actually much more complicated than people think. An OS could alternatively sometimes decide to do something like, I'm going to directly just take those pages that I already have in physical memory and just map them into your process. No copy, no faults. If it does that, it would be basically instantaneous. And so all we're trying to do here with doing these tests is to just probe the operating system a little bit, see what it's doing, and make sure that whichever path we're using is the fastest path that we can find for this particular OS. If that makes sense.
Yeah, it absolutely does. All right, so then let's continue a tiny bit. So roughly buffered input stream and file channel are roughly around, it took roughly around the same time. The difference between these two APIs is that actually with the buffered input stream API, I just get the entire stream, and I can actually skip bytes, but I cannot say open up the file and from a specific offset start reading, specific bytes. And with file channel, I have that flexibility. I can just, go to a file and, specific offsets, read chunks from that. And that's why I actually went with the file channel API going forward.
And that seems like a good choice because, like you said, we want to multi-thread this eventually, so we're going to want something like that.
Yes. Now, let me just briefly run you through the file channel code again once more. It's a bit of Java API here. So we open up a file channel to the measurement.txt file. We allocate a byte buffer, which is 10 megabytes large. The byte buffer for you is simply kind of a wrapper around an array with some convenience functions. It keeps track of the actual position we're in, the limit of the bytes, and just gives you a couple of functions to extract stuff from a byte buffer. It's just, a convenience around a byte array, convenience object. And here what you can see is the method, what it does is essentially just, keeps on reading into the byte buffer until we read in the entire file. So that was, the speed test we just did. Now, I wanted to go one step further because we have reading in the file. And the next step in the challenge would be, hey, we want to go through the individual lines, obviously. We want to find semicolons in these lines. We want to find new line characters in these lines. And we want to think about, splitting out the city as everything which comes before the semicolon and the temperature which as everything which comes after the semicolon and until the new line, right? Mm-hmm. Okay, now let me just walk you through what I tried to do here. I'm just going to uncomment.
Could you just really quickly before you go on to that, for those of us who don't know, which includes me because I don't program in Java as we've talked about in previous episodes.
Yep.
What is flip and clear? Because that looks like operations on the byte buffer.
Yes.
And so is this a double buffered byte buffer or what's happening there?
So the thing is, we're reading from a channel here, which means we're writing into the byte buffer.
Okay.
And writing into the byte buffer sets internally, the position of the byte buffer and the limit of the byte buffer. It changes these things.
Okay.
And it's in terms of Java API, what flip actually does is it resets the position of the byte buffer to 0 and the limit, and it makes it available for reading from the byte buffer.
I see.
So it's purely this is just a purely standard way of how to interact with byte buffers in Java. You read to it, you have to flip it, then you can, you write to it, you flip it, then you can read from it.
I see. So basically this read sort of fills up the byte buffer and we're sort of like at the end of it or something.
Yes.
So the flip kind of rewinds us and it lets our reads start at the beginning. Oh, I see.
Yes.
Okay.
All right. And actually what I wanted to do here is I didn't want to go through the byte buffer. I didn't really care about the byte buffer itself. I'm getting the backing array, the byte buffer array here, and I did everything directly on the array itself and not use all the convenience methods around it. That was what I wanted to do. Okay. So we've got the array. So we've got like 10 megabytes. My thinking was, again, we got 10 megabyte blocks, and I don't know where the 10 megabytes end. So they could end in between a line or after semicolon or whatever. So I'm getting these 10 megabyte blocks, and then I'm trying to find the last new line character. So I'm just going backwards in the 10 megabyte block and using that as the real end of the block. So I can actually write a very simple, parser, and I know it just, ends on a new line character as opposed to in the middle of a line. That's what I'm trying to do here. Okay. So I'm just going to the array, going backwards from the end. Hey, give me the last new line character, essentially. And then I'm just traversing through the entire 10 megabyte block here and saying, hey, give me the next semicolon in the array from my current position, rather. Then give me the next new line character afterwards. And then again, semicolon, new line, semicolon, new line. So we just step through the entire 10 megabyte block and we find the semicolon and new line characters.
Yes. And
just to show you once, the find method does nothing, so it really just goes from the position that you put in and tries to compare whatever is in the byte array at the specific position. It compares it with the semicolon, or it compares it with a new line character, and then it just returns, returns that. That's it. So there's no magic happening at that place. All right, so we've got that, and now the interesting thing is, I asked myself, we had 1 second. Yes. And I ran this before. And I was wondering myself, how fast would it be, or how slow would it be?
So am I, because again, this is the part of the thing that I'm excited to see. I want to see how slow Java is at some of these things when you just type in what you would expect, right?
Yeah, can I ask you now, just out of interest, what would you now reckon? Just finding these semicolons, newlines throughout the entire file sequentially. I mean, just a single threaded. What do you think now is going to happen? So we had 1 second, roughly 1.1 seconds before now on the baseline. What do you think it's now going to show? I mean,
it's really hard for me to guess because I just don't know what kinds of stuff. Like, is Java going to compile this code, I assume, at this point? Like, I assume Java JITs are sophisticated enough now that it's going to try to compile this down. It's going to be doing direct, like, I'm assuming it's not going to read the thing multiple times or any of these sorts of things. But I just don't really know. Like, because I don't spend any time programming Java, there's so many things that could go wrong here.
Let me click the button and we'll see. We'll see what happens.
So I have no guess because it could be arbitrarily large, really, depending on what it decides to do here.
Yeah, let's see. So it's still running. It's still running. Again, the naive solution, just to tell people, is going to take you. It took you like 90 seconds, or just reading the lines at least 33 seconds or 34 seconds. Now finding these characters roughly, let's say, 11 seconds.
Gotcha.
And then I thought, hey, for a while, I looked at these numbers and thought 11 seconds. So just, finding these finding semicolons, newlines adds an order of magnitude. I don't know, it adds 10 seconds to it. But at the end of the day, I also thought, well, we're literally processing 13 billion bytes, comparing them. And maybe this is what we need to expect from a single-threaded application, which goes through all these, because it's a lot of instructions for the CPU. And then I thought, hey, these 10 seconds, these 10 additional seconds, they actually don't sound that bad. So, yeah.
Well, I think in terms of, not actually sound that bad. Yeah. So one of the things that we want to do is just put into perspective how long 10 seconds is, right? Mm-hmm. And so if you have I don't know if you have a way to count the number of characters in this thing, but basically the bytes, the size of the file, just in raw bytes, that's how many characters there are, right? That's how many, because this is UTF-8 encoded, but we're stepping through, it really didn't use that much. So we're roughly talking about that, and even if we weren't, characters is not as important as bytes because we have to process two to process that character, right? To process like a UTF-8 more complex character.
And because it's 13 gigabytes, I thought, if I'm not mistaken, it should be then 13 billion bytes.
Exactly. It's going to be, whatever the actual total number is there, right? Yeah. And we also know that you're running this on a MacBook. I don't remember. You said it was an M2 or something like this?
It's a Mac Pro. This one is a Mac Pro M. Let me just quickly, briefly double check. We'll see. An Apple M3 Max, if you can see it here.
An M3 Max. Okay, so let's just do this exercise because I think it's good for people to see. Yeah. So let's use the internet or wherever you want to look up what the clock rate is of that Mac M3, that the processor you're on, right? Or you can even, if you know how to do it using like the command line or something, you can even just get it from your system directly. But any way you want, get the processor speed. Okay, so there it is. It's over in the corner, 4.05 gigahertz for a performance core. Now, we don't know if we're running on a performance core yet because maybe there's some weird thing that's causing us not to, but we do know what the maximum could be. So if we are correctly allocated performance core, it's 4.05 gigahertz. So open up a calculator and 4.05, right? Times 1,000.
You might have been confused with the comma and with the dots, but in German it's commas and times,
1,000.
1,000.
Times 1,000.
Times 1,000.
Times 1,000.
Times 1,000.
And that, right, is going to be 4.05 gigahertz. That's how many instructions how many cycles this thing has to dispatch instructions every second, which is less than the total number of instructions it can do because it can do multiple per cycle, which we'll get in a second. So this is just how many clocks per second we're getting. Now we multiply by 10.959, which is how long the thing took.
Yep.
That's how many just machine cycles we have. Now, divide by the size of the file, which we can look up in the, you can do an ls on it and just literally get the number there. So just divide by that.
Right.
That is the number of cycles, right, that you could do per byte on a single core. And on a single core, depending on the circumstances, you get a certain number of instructions per cycle that will be dispatched. 2, 3, 4, something like this, right? So that means that we could probably expect to be spending, for every byte in the file, we could spend at least 3 cycles just on that one byte, which means we can probably execute, 10 instructions, let's say, per byte in the file. Now, every instruction we execute, because Mac is a SIMD, it can do multiple bytes. Every one that we execute could be operating, say, 16 bytes wide if it wants to, too. So when you multiply all these things out, you're like, okay, literally I could be spending something like 10 instructions per byte in the file. And that would be if I didn't even use a wide instruction, which could have been handling 16 bytes at a time. It's not looking very favorable here, right? Because all you're doing is one ask on it. You're just saying, is it this thing? That's it. That's all you had to do. You're not changing it. You're not doing anything else. So to answer the question of is this reasonable? It's not like that number came back 500, in which case we'd be like, nowhere close. But is it anywhere close to optimal? Almost certainly not, right? Because, again, to put this in a little perspective, assume that we were using wide instructions to do our testing or something like that. You would multiply this number by that byte size, like times 16, right? And that's basically how many instructions you could do per byte because you're operating on a big chunk, right? So it's not looking great. That seems like we're spending a lot of time doing things we probably don't need to be doing, or we're suffering from just the speed at which the memory comes into the CPU. So that's why, I just want to do this one first, because you asked about this.
Right, yeah.
So at this point, we don't know very much. It could be that the Java VM, when it does its JIT or whatever it's doing, is producing code that's it's not quite that efficient. So it is just taking 3 cycles per byte to process this information, and we just need a way of writing the code more efficiently. Or it could be that we're not getting the information into the CPU fast enough because we're just reading directly out of memory. And so there's all this extra stuff going on. So let's talk about that second part. Getting the data in, we have a kind of unique situation here. This is coming from a Ramdisk, so we know that what we're doing is effectively a memory copy unless the operating system just maps it in. Now, we know the operating system isn't just mapping it in because it wouldn't have taken 1 second, it would have taken 0 seconds. If it just mapped it in, it would have been instant, right? And then we would have had a different scenario. In this scenario, we know that the operating system has to copy it in. What that means is the operating system has to read each byte and write each byte, right? It has to read it from the RAM disk, which is, it's sitting in physical memory. It has to read it, and then it has to write it into a new place in memory that's for your process. It's doing a copy, right? And that copy is copying into your buffer, that 10, megabyte buffer that you made. So we also have to account for that, and that, you have to, and then you are going to read it again. So it's a read, write, read. Because of that alone could be the thing that's slowing us down because that memory traffic might be much more costly than the act of scanning. So the first thing that we want to do here is to see what happened if you timed this. I forget what the time was. If you timed this without actually doing the scan yourself, what did you get?
So without just the, you mean the scanning for the, right?
That's great. Like just what you just did.
Yeah.
Okay.
1.2,
so,
1.1, let's say, along these lines, Yep.
So if that is to be believed, though, it's kind of hard for us to tell here because I guess I don't know. Is there a way for us to easily determine that this code hasn't been optimized out. Like one of the problems that we're going to hit now as we start to actually try to drill down towards solutions is I don't know how wily the Java VM is. And so when we do a timing like this, we don't really know exactly what code was being analyzed.
Yep.
So in normal situations, what I do is I just look at the assembly.
Right. Yeah.
I just look at what it is.
Yeah.
Is there any way we can get a clearer picture of what the code is literally doing here?
There is a way, unfortunately, not for today, and I'd need to do some proper preparation to actually find that out.
All right, so let's start our homework list then, because I think we're in a good shape to do that.
That's going to be a rough homework list, to be honest. It could take me a while, but yeah, please let's go ahead. Let's see what. Let's write it down. Okay. Mm-hmm.
Yes. So one thing that we're going to need to do, and again, because I don't program Java, I don't want to specify exactly how you would do this, because we just need some way of knowing what we are actually executing. And there's two reasons that we want that. One is, like I just said, I would like to be able to see if code is actually running or not. Because sometimes we do a timing and we think we did something very fast, but really what happened was because we are just doing test code and we're not really producing any tangible output sometimes, the compiler can go ahead and remove a huge section of our code. And so what we really saw was the effect of not producing the output.
Right.
So the first thing we want is some way to do that, and that allows us to test better. The second reason it's nice to be able to do things like look at what assembly we're actually running is because then we can ask questions later on down the line when we get a little further in this, maybe 2-3 episodes from now, when we're trying to do some micro, right? That'll let us ask the question, what is the Java VM actually generating? Because that will tell us why it's slowing down, right? Because we can see, like, it chose to output this way, which is not the optimal sequence. Is there something we can, finagle on the source code side that will make the Java VM produce the thing we want? And believe it or not, this is actually one of the most common things that even the hardest core optimization people do. This is not something just for beginners or anything like that. One thing that people often will do who are very good at performance is they'll have those two things. They'll be changing the code for the compiler. Usually it's not Java necessarily, but it's C or something. But even if it was Java, you're tweaking the code to try and massage the compiler into generating the sequence is optimal. And the reason you're doing that is because you don't want to have to hard code the result in assembly language, which makes it harder for people to read and harder to modify later, and all those. There's all the reasons why people moved away from assembly language. You're trying to preserve that benefit while still getting the optimal sequence for that compiler. So that's the other reason we might want that. Does that make sense?
It does make sense. I have a question though. So,
Please.
and this is, so at the end of the day, the code I wrote in terms of Java is relatively low level for a Java programmer. Let's call it like that. And then even if I found something in the assembly output, my question would be, how could I even still, what else could I do apart from writing this, which doesn't make it look like C, for example, at the very end then? I mean, because it feels like my hands are kind of bound or tied here, because I can't really do much less because I'm already at a relatively low level of my Java coding here. Does that make sense?
There's a number of things you can do, right? And this is about sort of... So let's take something like Godbolt, right? The compiler explorer, godbolt.org. I assume most people have seen this. So suppose you have something like that, and you can load up a Java VM in it, right? And say, okay, JIT me whatever you're going to do for this code, right? And you look at the output. If you've done that sort of thing enough, you start to learn things that the compiler will do based on what you've written. So I'm going to give a very simple example. I'm not saying this is true because I don't program in Java, but let's say that in general, the JVM will not inline a function. If that's true, that find will result in an actual call, right? Out to a thing. Not only a call, but a call to something that throws an exception. If I remember correctly, I saw that in there, right? So it's going to have to set up an exception frame and it's going to be a real thing, right? If it doesn't inline it. So if we saw that happening in the assembly, we'd be like, oh, let's just copy that code in here, right? And make sure that the compiler knows it can just do the array check directly, right? All sorts of things like that you can do. And when you start to learn what the compiler's output is, you start to know like, oh, these are the, when I care, right? When I don't care, I don't care. When I do care, this is how I will write my loops, and this is how I will do, etc. And because we've seen people get very fast times by comparison on the leaderboard, by comparison to 10 seconds, right? They were getting 1. Now, maybe that's the machine, right? Because
because they were all multi-threading, so we could.
They're all multi-threaded.
Yeah.
So we don't really know. It could be, at this point, it could be just like, oh, if we, this is as fast as it gets and when we multi-thread, it's fine. It could also have nothing to do with this. Like I said, it could just be memory traffic, which we're going to look at in a second here. But because we know we're not at some amazing speed time here, there's still reason to want to do the investigation because we just don't know yet. Once we know, then we may say, yeah, okay, it's generating, like, we can't get the JVM to generate anything more efficient than this, so don't bother, right? And that's, again, learning that we need to have.
Right. Got it. Okay. Then I'll try to find something out here until next episode. It could take me a while, but I'll try to make something happen.
I can try to look too and see if I can find anything. I can ask some friends because I know people who do Java optimization kind of stuff, and I'll just be like, "What do you do for this?" Okay, so let's.
We've also, plenty JDK people at JetBrains, so I might just ask them as well.
Yes, that'd be great.
But, yeah. It's just not my specialty.
So let's ask the question about the memory, though, because like I said, this is going to be very important, and it could just be something that we're hitting right away. So before we even need to think about how fast those searches are, maybe we need to start looking at how the memory is moving through. And so let's talk about that a little bit. So if we assume that the processor is having to do what we said. It has to do a read and then a write and then a read for every one of these bytes, right? It reads it out of the Ramdisk, it writes it into your buffer, and then you read it again to check to see if it's a semicolon or whatever you're looking for, a new line. So if we're assuming that, then we have an interesting question. And that question is, what is the optimal size of the buffer that we're using to transfer? Because if we pick a buffer size that is too large, then the data will not still be in the cache. The operating system will read it, the operating system will write it, we will then read it, and all of that will be going through actual memory, right? It will actually, it will have to be a read, write, read, all of which are at the slowest possible speed, which is to memory. So what we also might want to try to do, if we can, is see if we can pick a buffer size that allows the operating system to read it from memory, which it has to do because it's too big to fit in a cache. 13 gigabytes not fitting in a local CPU cache. But it could read, then when it writes, it could write it into a cache. Then when we read, we'd read it from the cache, right?
How would you approach that? I mean, finding the correct buffer size.
Now let me say one more thing, because what we're going to do is try to find the correct buffer size. So the only reason that I think that this is probably not quite our problem just yet is and again, and this is also why I asked for that assembly stuff and to kind of look at what's going on, is that if it's really true that this file is getting read, write, read in just 1 second, then there's no chance that that is the problem because we're seeing 10 seconds, right? So the timing so far, if they are to be believed, and again, it could be because it's not something that if they are to be believed, we would not expect this to actually be our problem currently, right? So does that make sense?
Yeah, it makes sense. It makes sense.
So let's talk about that part as well, because we're going to want to do both of these. And so our homework for next time is like to start on one of them, right? Whichever one we choose. So the first thing we would want to start with is just knowing what the cache size is of this machine, which should be pretty straightforward. The cache, in fact, it would have been like on that Wikipedia page. In fact, if you want to pull that up again, we can actually look at it. But, there's also on the Mac, there's a command line you can type in that will tell you what it believes the caches are, which is handy. So there you can see there's a 192 plus 128 K per core under performance cores for L1 cache.
Let me just make that a bit bigger.
And there's a 16 megabyte for... oh, wait, you're a max? Was yours a max? M3 Max, I think you
so.
had?
I think so, it was,
So 32 megabytes of L2, right? Mm-hmm. So what do these two things mean, just for people who are new to this? Yeah. Well, on every processor, the cache architecture is different. So you can't really, unfortunately, without knowing a little bit about the system architecture, you can't necessarily know what it means when you say L1, L2 cache. On an x64, for example, let's say we're on the PC, the L1 and L2 caches are both per core. So each core has its own dedicated L1 and L2 cache.
Right.
The first time cores start sharing cache is at L3. And that's what we call an LLC, the last level cache. It's the furthest thing out. It's typically shared amongst cores, and it typically is responsible for coordinating like memory traffic between the cores. Mm-hmm. Not always true. You can have last level caches that are actually per core, and they use message requests to get it, but it's not important here. On the M series, that's not the way it works. On the M series, they only have the dedicated L1 cache. There is no dedicated L2 cache per core. So the last level cache on a Macintosh is actually the L2, and there is no L3 at all, right? It's not a thing. You'll notice it's not listed here. So what does this mean? It means that when we talk about cache that's specific to a particular core on the CPU, you can see what if it's a performance core, it's 192 plus 128, which we'll talk about what that means in a second. And then for the shared across all our cores, it's this 32 megabyte number there. So that means, for starters, we know that we can't use a buffer larger than 32 megabytes and ever have it fit in cache, right? Because that's the hard limit there of like things that, in the L3, that's the biggest, it could ever possibly be. And then for the L1, if we want it to fit in that, which is going to be faster because it's local to our core, if we wanted a buffer to fit in that, it's 192 plus 128. What does that mean? Which number is it? Do I add those two together? Like what's going on there? When you get inside the core like this, there tends to be, because it's very much about where these caches are placed on the actual physical CPU. Are they close to the instruction dispatch? Are they close to the register file, right? So what they do is the cache is typically split into cache that holds instructions and cache that holds data. Because remember, your program's running, that is part of the fetch, right? That's something that has to come in. And so the 192 plus 128 is telling you how much instruction cache there is and how much data cache there is. So we don't get both of those. We only get one of them. And my assumption is, because my recollection is that the instruction cache was larger on the M2. It'd be nice if it said, right, which it might in here. Yeah. My recollection is it's 192 I cache and 128 data cache. And that would make sense based on the numbers. Right. So my assumption is we have 128 in terms of our data cache. And so if we wanted a buffer to fit in the L1, unfortunately, it has to be smaller than 128, right? It can't even probably be exactly 128 because, remember, other things, all the data, our stack, like our program stack, is going through that L1 cache. So if we max out that L1 cache, that might not be a great idea either. So, you're talking about something that has to be a little bit smaller than that, potentially, depending on the circumstances. So that's the first thing you want to do in your machine to start understanding where these performance pitfalls might be on any particular architecture is to go, okay, now I kind of have it in my head. What are those vague jump points? Does that all make sense?
It does make sense. I learned a lot just now. Okay. Yeah.
So, like I said, if you don't happen to have a lookup on Mac, there is a command line. You could look that up, exercise for the reader. There is a thing that will tell you what the cache sizes are on your machine. It'll also tell you the cache line size, actually, although it's a little bit misleading because the L1 and the L2 cache lines on M-series chips are usually different, which is a thing that throws people for a loop. But anyway, that's much more advanced stuff. We don't have to care about that for this. So when we're looking at this, that means there are some things we might want to try. If we were going to go probe this, again, because we're trying to learn here, and also we're doing a challenge, so we're hyper-optimizing. We're not just, getting it in the ballpark. What we might do is try these reads with like a loop, basically, like a thing that sits there and does the timings, tries reading the file in various ways. Like, let's try a 32K buffer, a 64K buffer, 128K buffer, 256K buffer, 512K buffer, 1 megabyte buffer, right? Then let's jump up 60 megabyte buffer, 18 megabyte buffer, 19 megabyte,
Right.
Whatever you want. Like, pick a bunch of sizes. And what I like to do is just graph them. Have it output the thing in a little like nice CSV. You could load into a spreadsheet program or whatever you want. And usually what you'll see for any algorithm that you're testing this way, assuming that you've got a good test setup that isn't missing some crucial, aspect or something, is you'll see a cliff. There'll be an obvious place where you're just like, oh,
Right.
boom, I dropped off a cliff right there. And that's how you know for any particular architecture what that optimal buffer size is. And usually what we would do, if we're trying to deploy this across a heterogeneous series of architectures, is we leverage the fact that generally speaking, cache behavior tends to get better over time. So we would take one of our minimum spec machines, we would run this fairly thorough testing on it, and we go, okay, that's the largest buffer size that we can afford if we just want to deploy, one code path through everything. If we want to be fancier, we can extend it to say, we could run this at runtime and adjust our buffer size, or we can just run a few on representative and do some testing and say, okay, we're going to run it on this class hardware, this on this class hardware, and go from there. So that's how this works. For our purposes, we would just be doing it for education.
Yeah,
We're
right.
trying to learn what happens with the Java VM here, right? So we would just be doing it to learn what's going on so that we can craft our algorithms. Does that all make
Right.
sense?
It does make sense. But I'm just looking at my homework stack and thinking, shit.
We're only going to do a little bit of this. We're going to pick like something to do.
Yeah.
So that's how that stuff works. And again, based on the fact that it jumped, if we really believe that we're reading in the entire file in 1 second, right? Then it doesn't really stand to reason that, because that's a read and write for the operating system has to do. It doesn't stand to reason that just adding one additional read at that point, it doesn't make sense why that would jump to 10 seconds. So that suggests to me that it's not just the memory traffic, just because of the timings that we've already seen. Without even looking at the memory specs for this machine, which is a thing we will do later when we're trying to optimize that.
Right.
There's really no reason for us to suspect that we aren't wasting time, again, because of that. So it feels like the Java VM is generating inefficient code for that loop, and we should be able to get that down to, let's say 2 seconds or something, if we were just at the memory traffic speed, which is, I'm just picking double the time of what the operating system did for its read-write.
Okay, got it. Right. Let's continue that journey. Let's see where it leads us to. Yeah.
Okay. So I would say the best thing to do next time, honestly, is to see what we can do about that top part. Not the buffer sizes, not the graphs. Just can we get something where we can look at what the output is of this thing? And even if all we can get is like something that tells us whether code will get optimized out or not, even that would be a huge help to us, because then we can just be sure as we're doing this testing that we're testing the right things. But if we can get actual assembly, major thumbs up. But if we can't, then that's just that indicator is all we really need.
We can easily get the actual assembly, but I need to do some preparation for that. Yeah. Okay. Cool. Then thank you, Casey. Let's wrap it up for today. And then next time it's going to be assembly time. Interesting. Yeah.
Yes. And I would really, really suggest that people not be scared of assembly. I know everyone is.
Yes.
But the truth of the matter is, assembly is incredibly, incredibly simple. That's the nice part about it, because it's what your CPU is running. And so it can't be that complicated, because it has to be very straightforward for the CPU to be able to execute it, right?
Right.
And so it's much simpler than something like Java. Like, understanding Java is... There's so many things, like you just saw there's 4 file APIs or something, right? That you were looking at there or something like that. Assembly language is not that way. There's usually okay, here's some things that add numbers. Here's some things that, jump if something's not true. It's very, very simple stuff. And once you learn a few of them, then you can at least read the assembly and go like, oh, okay, it's doing something reasonable, or, what the heck is this? Like, you just see this big pile and you're like, okay, I don't even need to read that. I know something's gone horribly wrong. Let's try to trim that down, right? So it's easier than people think, and I'll try to walk you through it a little bit.
Okay, cool. Let's do it. And thank you very much, Casey, and see you next time.
Okay, see you next time, Marco.
Bye.